everybody. Reporting to you again from the Glamour City, Hollywood.
Our perspective is that, a network engineer doesn't want to learn how quantum memory works. They're not a quantum experimental physicist, but they want to be able to say, hey, I'm trying this new protocol on top of this memory. How is it going to behave? So can we actually replace the real behavior of what that actual memory will do with something that is equivalent for this network engineer to actually play around with it? All of those communities have said that in order for us to make a massive investment in the type of infrastructure you need for a quantum network to come online, we need to see metrics, we need to see tests. And even for a test bed, we need to see some tests to enable a big test bed.
If you love listening to this show, please consider giving a rating and a review on Amazon Alexa or wherever you listen. We want to continue bringing you this amazing content, and part of our ability to do that means that we need a big audience. Now, it may not seem like much, but rating and reviewing the show will help more people find us, just like how you found this show. Simply on any podcast platform, search for a show, scroll down to the bottom, and push 5 stars. It's that easy. Thanks for supporting the show. I'm joined by Dr. Prineha Narang, Assistant Professor of Computational Materials Science at the John A. Paulson School of Engineering and Applied Sciences at the Harvard University. And she's also the CTO at Allura Technologies. Welcome to the show today.
Thank you so much, Scott, for having me here. And I look forward to a great discussion on quantum technologies, where the field is going, and any questions that you and your listeners have.
Well, your work has been recognized by many awards and designations, including the Mildred Dresselhaus Prize, Basel Research Award from the Alexander von Humboldt Foundation, Max Planck Sabbatical Award, and many more. So if you could tell us a little bit about your research work and some of the bodies of areas that you look at, and what's led to some of these specific recognitions and awards.
Sure. So I'm, of course, delighted to have received these awards, be considered for these. My group works at the intersection of quantum materials, thinking about kinds of materials that can have an impact in quantum technology. We think about new ways of predicting the interactions in these systems and how it intersects with new types of quantum information technologies that we can make possible. So put this another way, I started out as somebody who is purely thinking about computation from a physics standpoint, realized that cloud computers were right there available for us to start using, even in their preliminary form, and incorporated that into our toolkit here. So it's this area, I think, it sits at this boundary of a couple of different fields, and it's been fun to work in. I think that what some of these recognitions and things have afforded me is an opportunity to work on problems that would not be traditionally funded by federal agencies, work on topics before they become popular, as cliche as that sounds. So, and that's what we do in my group. There are students who join my group who come purely from a physics or computer science background, some that come from a very applied engineering background, some that come from a chemistry background. And we bring that very diverse lens to the problems I just mentioned.
Well, it's truly frontier work. And of course, to your point, it's a very multidisciplinary approach. And of course, you're referring to your Narang lab that you're referencing. Can you tell us about some of the specific sets of research and developments that you've either published or have worked on recently?
Yeah. So my personal favorite is our recent work in cavity control of quantum matter. This is using optical or terahertz cavities to actually modify the behavior of matter. And this is essentially a way to create new non-equilibrium phases that would not exist in the comfortable state of these systems, and to use these then in various technological contexts, whether it's a control of the magnetic order, control of the superconducting order, and other ways that these can become relevant, even in, for example, energy technology. So we're very fundamental, and our focus was very much on, where are the gaps in a theoretical understanding of such cavity control of systems. And we started to develop a new theoretical framework to actually address this problem. Quickly realized that there were, fundamental reasons why something like this didn't exist. And working together with a couple of my postdocs, we released a framework that actually allows you to treat photons, the matter component, as well as finite temperature effects at the same level of theory. So rather than including it ad hoc or introducing discontinuities because you're not treating it at the same level of quantization, we were actually able to do it very rigorously. So pretty psyched about that. And I know you said this is a deep tech audience, so hopefully that didn't get too deep tech for the audience.
I think it was fine. And I was looking at some of your other paper as well. There was one that was released last year. It's called Computational Materials Insights into Solid State Multi-Qubit Systems. And I think in it, you talk about the need to focus on quantum computers around scaling and integrating new solid state qubits. Can you tell us a little bit about that? And again, I think it does get into a little bit of theoretical aspects, but the paper shares a perspective on the modeling and rational design of multi-qubit systems.
Right. So I'm glad that paper in PRX Quantum is being read. Our view on this was that there's a lot of emphasis on how do we take existing known qubits and optimize them. But there's an opportunity to bring new material-based qubits into the field that allow you to actually surpass, the best you could do with existing, say, diamond or silicon carbide-based technologies, or even some of the silicon-based platforms that folks like people at Intel and others are commercializing. So towards that, we said, well, how would a theorist or a computational person make this possible, right? Some of the things that we know now about say diamond-based or color centers in diamond that have shown a lot of promise. Well, it took over a decade to get it from somebody first saying this is an exciting spin qubit to actually now the first few startups being launched around it. So as a theorist, I say, well, we don't have that kind of time. We want to actually make this cycle much, much, much faster. And the way we can do that is if we have a fairly robust and rigorous theoretical framework for actually predicting not just single qubits, but their behavior as coupled multi-qubit systems. That's how they would be used in practical applications, and be able to link those fundamental studies of few qubits to what a scalable architecture that's based on these looks like. So a concrete example of that is that if I'm using these defects, I'm thinking of them as spin qubits that act as a quantum memory. There are various ways I can use it and types of protocols that would live on it from an architecture standpoint. It could be in the context of a QRAM that is attached to a quantum computer. It could be a memory that sits in a quantum network. And the constraints you have for those two scenarios are totally different. And this is a problem for theory and computation. This is something we can do instead of an experimental. I love my experimental friends. And for those listening, I absolutely admire the work you're doing. But as a theorist, we can actually really speed up that trial and error cycle that exists in actually taking some of these qubit technologies out of the lab. So that's what we put forward. This is actually a paper I wrote with one of my prized postdoctoral scholars who's in my group, Dr. John Philbin. And we spent a lot of time analyzing, the literature out there. How had people taken a first new material discovery of a qubit and how long did it take for it to actually become a technology as you would see it? And that's where that paper came to be.
I think you bring up a very interesting point. And of course, there's always that bit of friction between experimentalists versus theorists. But at the same time, it's interesting because I think you bring an interesting point, which is that theorists can actually speed up commercialization. And you're actually, matter of fact, in your current role at Illera Technologies, you're actually playing that role as well. So if you could talk about a little bit about how theory actually helps speed up commercialization and maybe the genesis of Illera. And I believe that's spun out of Harvard as well, right?
That's right. Alira emerged from my group, and I have just been so excited to have the opportunity to be, part of the commercialization journey of quantum networks. And one of the ways that theory and computation is having an impact there is that within Alira, we've developed a robust platform for both simulation and emulation of quantum networks. Now, to this day, we have detailed emulators, even of classical networks that exist. That's how we think about managing traffic, congestion in networks. That's how we actually debug some of these networks. That's super important. And for quantum networks, something very similar was necessary in order to actually speed up the creation of these both small and eventually more complicated networks. So, for example, you are a very hypothetically, a vendor who is making new nonlinear optical components. You want to see how your component, substituting that in the larger network context, is going to actually change the performance. So you could do that. You could work with a test bed, and some of these are just now coming online. But your first thing to even get into that test bed would be able to say, hey, here's how within this very complicated sandbox at a system level, I think my little widget is going to have an impact. And that's exactly one of the things that our platform enables. We decided to go down this path of actually making our own very detailed simulation and emulation platform, not because that's our eventual product, but we recognized that there was a whole set of people out there who just had no way of estimating how making one small change to a component of a quantum network would actually change the behavior of a protocol that sits on top of it. And I think that's an example of where theory is really accelerating the arrival of a new quantum technology.
Yeah, this is incredibly not only fascinating, but incredibly economically valuable because as a VC, we don't want to necessarily, continue to inject in hundreds of millions of dollars or even billions for experimentation that's going to fail. To be able to have some level of simulation and emulation, be able to have predictability in terms of how it's going to actually net out, that's incredibly valuable. Can you quickly distinguish the difference between emulation versus simulation?
Right. Yeah. So simulation is where you're looking at the expected behavior of something, and you're parameterizing, how you expect some of those components to behave. In the context of emulation, you're looking more at the functional behavior of your system. So you're say looking at equivalent fiber. So it's an easy example of emulation. I may not have 200 miles of fiber sitting in my lab, but I could have an equivalent spool of it that is allowing me to emulate how something is going to behave over those few hundred miles. And I could do various types of things to it where I can say, okay, the temperature as it varies, maybe I can collect all of that data and incorporate that now into my simulator to parameterize some of those models. So that's where that expected and functional behavior of a network aspect comes into play. Emulation can also become quite important when you're thinking of the behavior of various, quantum memories. So that's another example of where there are various quantum memory platforms out there. Some that sit inside a dilution refrigerator. Some people say are actually more quantum room temperature. And for each of those, our perspective is that a network engineer doesn't want to learn how quantum memory works. They're not a quantum experimental physicist, but they want to be able to say, hey, I'm trying this new protocol on top of this memory. How is it going to behave? So can we actually replace the real behavior of what that actual memory will do with something that is equivalent for this network engineer to actually play around with it? And that's the type of stuff that Alira is doing already. We're doing this for various customers, including a big utility company. I can't name this yet publicly, but that's one of our customers. We're also doing it for various parts of the Department of Defense and the intelligence community. Again, I can't add too much more color to that, but all of those communities have said that in order for us to make a massive investment in the type of infrastructure you need for a quantum network to come online, we need to see metrics. We need to see tests And even for a test bed, we need to see some tests to enable a big test bed. And that's what we're doing. Yeah.
Well, again, I can't get, I can't express my enthusiasm enough. I think whether it's a very large publicly traded company or a startup, from a CEO and CFO perspective, this is a hugely valuable tool, and be able to have some level of, I wouldn't say assurance, but some quantification, empirical data set that you can start to, put some teeth into, and so that you can make the proper, investment decision in terms of, to proceed or not to proceed. Now, with that said, I think at the heart of what Alira is doing is this notion of quantum networks. And I believe you have made an assertion before that in order to get to say 1 million qubits or larger size quantum computing, it really requires being able to cluster moderately sized quantum computers. Sometimes, again, this is referred to as clusters or distributed computers for the time being. Can you tell us about that and why that is so important?
Sure. This is actually one of my favorite topics. When people are trying to scale up quantum devices, in some ways, it's almost a paradox, right? You're saying there's a very pristine quantum-only state that I'm working with, but you're now saying a scalable quantum version of it, which suddenly starts to look very messy. A lot of decoherence comes into play. It starts to become very quickly a low fidelity, high error rate situation. And instead of fighting thermodynamics in that context, what you can do is break up the problem and say, hey, I'm going to have devices of a particular size where I know I can robustly make each one individually. I'm going to connect them over a network mesh of some sort. Now, if I connect two quantum devices over a classical network, right, say I have X qubits and Y qubits in another system, they don't even have to be of the same qubit modality, actually, and I'll come to that here in a second. If I connect them over a classical network, I don't have X plus Y or even X plus Y minus losses. I have X and I have Y, because ultimately going over a classical connection for those two is not allowing them to actually share that quantum state quantumly. You're not actually connecting them in a way that allows you to make a single large quantum computer. Mm-hmm. However, if you connect them using a quantum network, a small quantum network, which, by the way, where you could think about a data center where some of these devices are co-located and they're connected over the equivalent of Mellanox for quantum networks. If you do that, suddenly you're not fighting thermodynamics and you're getting to scale faster. You're also looking at, and it's going from a particular qubit modality to another one, of course, involves that transduction step. It involves some way of connecting and then going to a photonic qubit, which is where you're actually able to connect these as a network, right? A flying qubit. That's it's not trivial, but it's a substantially easier challenge. And this is maybe my enthusiasm as a theorist. It's a substantially easier experimental challenge than some of the direct scaling ways that people are going about it. And I think in some ways it's complementary to those approaches as well. And you can think about combining the best of, say, superconducting qubits and trapped ion qubits, or superconducting and defect-based systems, where maybe one case you have fast gates, another case you have long coherence times, or in the case of defect-based systems, you could even use it as a QRAM in the future. So I think there are various reasons to do this. People are already starting to do it. And I suspect it will be a very prominent pathway to scale in the near future.
Mm-hmm, absolutely. And I think one of the things I'm kind of curious is, I wonder if this is the beginning of essentially kind of a quantum cloud infrastructure in some way. So that's really interesting. And then one of the things that you started to get into is the fact that it is not trivial. For the network to properly work, it needs to work across many modes and approaches, whether it's semiconductor-based superconducting, trapped ions, cold atoms, photonics, and many others. So being able to actually interface with any of these modes, I mean, that's really difficult. And I wonder, from both the CapEx, but also the operationally, how do you actually address that?
Yeah. So our focus has been to develop, if you think of the various layers of a network, we're developing the various layers in a way that is modular. So we have an orchestration and a control plane, and this is now a control plane in the sense of a network, not in the sense of a computing context where you're talking about actually controlling individual qubits. Something that connects all the way out to a network protocol that sits on top. And what we've been very cognizant of is that the hardware layer, the lowest physical layer, needs to be something that you can swap out. So we can't have a whole stack of this network become tied to a particular quirk of current hardware. And that in some ways incurs a little bit of a complexity cost, right? You're making something much more complex than you need today. So we've actually internally in our roadmap really traded off where some of that complexity is okay, even though it's unnecessary today, and where we intend to incorporate it as our own stack at Aliro becomes more and more complicated. And we are doing some of that integration of the hardware, but we're, again, being very mindful that we want to partner with various vendors. We don't want to become tied to a particular platform. We're helping accelerate who will be a future winner in this field, but we're not, picking a winner and putting all our eggs in that basket of hardware. And especially for quantum memories, this is important. Today's quantum memories are very, very early stage, but we, don't want to go to a sophisticated large customer and say, hey, you're going to get a memory from somebody else, figure it out, and we'll, integrate on top of it. We are actually, getting fully integrated solutions out there and telling people that, hey, in future, if a different memory becomes available, the rest of our stack will continue to work. And that's the only component that we will sub out for you.
So as I'm listening, the lens by which I filter it is very exciting, because to your exact point, which is an issue for investors, is we don't know exactly which hardware is going to play out. But the infrastructure that you're talking about, the abstraction layer that sits above that's hugely valuable, and that's going to be necessary and needed. Now, to that point, the critical infrastructure requirement for quantum networks, at least for the time being, is around optical technology. And I believe high quality optical fiber is the most viable option for today. But I wonder, as you're in the forefront of research, what are some of the other options that you're starting to see that could be available in the next decade or more?
Yeah. I think that there have been a lot of advances in optical components. I think finally we're starting to see even, large foundry efforts, some that are actually not based too far from where you are, dedicate their time to optimizing the process and quality of some of these optical components. So I think we will see, new and smaller footprint lasers that are relevant for quantum technologies in particular. We're going to see some things that help us with the loss in the fiber itself. Ultimately, though, I think regardless of how good your fiber is, there's still going to be some loss, and there's still going to be a repeaterless bound that shows up. So the requirement for quantum memories and quantum repeaters isn't going away. But I think some of the constraints on what those quantum components have to accomplish might become a little less tight over time.
Makes sense. Again, in my head, companies like Cisco and AWS comes to mind in terms of both partnership, but also strategic acquisition as well. Now, of course, when we talk about quantum computing, thing that's really on the top of everyone's mind is some of the challenges, things around, making sure the entanglement happens, maintain the coherence and the duration of it, the error correction, and of course, we've been talking about quantum memory and the reliable repeaters. What are some of the progress that you're seeing across different approaches, and what do you think is going to be kind of the more higher confidence pathways that you see?
Yeah, there have been a lot of advances, I think, in trapped ion and called atom-based computing technologies. I think that in some ways they're leveraging, decades of fundamental physics work that's gone on in various labs. So I've started to see, more come out there than I had expected to see by this point. Of course, IonQ has made a big splash. There are others. I think in terms of protocols and where we are with error correction on quantum computers, I mean, it's still a long way to go before we can talk about something that's either fault tolerant or can be error corrected. So for networks, when we talk about error correction, that's a different story. So networks, you actually don't have the same kind of resource overhead, and actually the pathway to being able to have fault tolerant and in some ways corrected networks is shorter and less fraught with fundamental risk.
Yeah, actually, that makes perfect sense. And certainly there's a precedence that you could look to as well. Again, I know this is a kind of a strange question, but we're starting to get into the topics of Web3. And it's let's say it's loosely defined as decentralized internet that starts to maybe minimize or puts less emphasis on centralized entities like the likes of Google and Facebook and so forth. In the context of Web3, how does quantum computing and the quantum networks could potentially play into that?
Various quantum devices that have become available on the cloud, right? They're readily accessible. People are, it doesn't matter if you are, a quantum information expert or just now learning your first few Python scripts to access some of these quantum devices. You can use them. You can get as much time on these as you can on any other compute platform through the prominent cloud services. And I think it's also making a set of algorithms that previously were not so mainstream, these hybrid quantum classical algorithms, much more mainstream. So this is where you're taking a problem and using the best of all resources available, whether it's GPUs, CPUs, or your favorite quantum device. As the user, you're figuring out, how do I divvy up my problem over these resources and get the best possible outcome? So I think it's changed the conversation from the very early, when the first devices were being made available to the public. Is it a competition? Is there a crossover point where we're going to see quantum devices take over? I think people realize it's going to be another compute tool that will help you address problems that are independently of interest. And you're going to do that with all the tools available to you. You're not going to be tied to just the one. And I think that's something that we're starting to see. So hopefully that gets to your question.
Absolutely. One of the things we talked about before the beginning of the interview was this notion of how do we figure out who are going to be the winners in quantum computing ecosystem. And I wonder, from your perspective, what sort of lens and what sort of frameworks do you use to figure out, is this going to be viable or not?
Yeah, it's in some ways now we have publicly traded quantum computing companies. So those are certainly easy to look at and say, okay, they're doing excellent work. Clearly, they're getting excellent valuations and they're fulfilling a need that the market has. I think in terms of new technologies or new platforms that people are just now announcing and saying, hey, I have a new qubit platform and I'm going to go out there and I'm going to surpass everything that's happened in some of these other technologies. Those are the ones I look at through a healthy skepticism lens, I guess, is maybe the phrase I'd use. It's cautious optimism, maybe put it in the positive, where I'd say, okay, sure. What's your roadmap? What kinds of fidelities are you expecting to see? What kinds of gates? And is there a specific problem that you have already showed on your quantum hardware that has been a struggle on some of the others? And that's the lens through which I evaluate a new quantum hardware play. Not necessarily a new business approach, but a new qubit modality that somebody is saying is going to be able to surpass everything that's out there. So I look for, what their roadmap is, when they actually will intersect, or have they already intersected and surpassed what's out there. And I also look very heavily for peer-reviewed work that the founding team has published, because I think with the excitement and enthusiasm in the field, perhaps some of the claims are said with a lot of hyperbole, and I think it needs to be tempered with looking at peer-reviewed work that has emerged from those teams.
Yeah, and I can agree with you in terms of the rigor that's necessary, and peer review is definitely one of the key areas that we would look at as well. Normally, by end of this point in the interview, we typically ask kind of lessons learned. But in lieu of that, I wanted to ask you a question, which is, you're incredibly accomplished, like we said at the very beginning, and we love to see more gifted, technically inclined women in your field. And I wonder if you had any type of advice for them that are listening potentially.
Certainly, I think my area of physics and also the subfields of quantum information doesn't have nearly enough women. And my advice to women, particularly students and postdocs entering the field, is don't be intimidated by that. You may not at the very first moment find people who you might not find the kind of representation that you would like to see. However, there is actually a lot of mentorship available in the field, and there's a recognition and various peer mentoring, as well as other mentoring programs that have been introduced, because we don't want to repeat the same mistakes in this new field that have existed in other fields of STEM. So, there are programs that are actually very heavily directed towards women entering the field, encountering challenges that perhaps are common to people who have either been there not that long ago or are themselves dealing with it. And those conversations, I think, are very valuable. So the American Physical Society, APS, organizes every year at their March meeting, the national meeting, a forum for people to actually discuss, women and other minorities, to actually get a chance to network and ask some of these questions of people who have been in the field substantially longer. The Materials Research Society offers similar opportunities. I think it's called by a different name, but it's primarily, a breakfast format. It's not as formal as knocking on someone's door and saying, "Hey, I have this question, problem. Can you help me?" It's a lower barrier to entry. And for those folks out there who are not attending these in person, there are certainly many online forums that are trying to address these questions.
Excellent. And thank you for sharing some of those resources. I have been joined by Dr. Prineha Narang, Assistant Professor of Computational Materials Science at the John A. Paulson School of Engineering and Applied Sciences at Harvard University. And she's also a CTO at Alira Technologies. Thanks for joining today. If you've enjoyed this episode, take a moment to rate our show on any podcast platform that you listen to. Scroll down to the bottom and push 5 stars. It's that easy. And as always, thanks for listening.